Hi guys, so welcome once more to our KC YouTube channel. So today we want to look at quickly the Therese pre-mock December 2022 physics paper 1, the part 1, which is basically the first 15 questions of the paper. So we just really want to quickly look at the problems and then the solutions and how you could have easily analyzed them. So if you also want to reach out to us, up here, that's our WhatsApp number. You can shoot us a message on WhatsApp or just shoot us an email through this email address. And also happy new year to every one of you. We hope that everything you've envisioned for yourself this year, you develop the courage, the tenacity, and of course the discipline to accomplish every one of them. Cheers to the life of your dreams. Let's dive in. Okay, so the first question goes: the force between any two masses m1 and m2 is given by F equals that the base unit of the universal gravitational constant G is. Okay, so the very first thing we have to do, of course, is basically just write out our expression and then basically make G the subject of the formula, right? And then replace every physical quantity with their base units and basically and see what gives us for G. And so our G is per kilogram meter cube per second squared, and so that answer is C. A body is moving in a circular path with a variable speed it has. Alright, so we're just quickly going to demonstrate the diagram of a particle moving in a circular path here. Now, the very first thing for you to note is that whenever a particle is moving in a circular path, it has acceleration, whether it's moving with constant speed or with a known constant speed. In that case, a variable speed, like the question is talking about. So if it's moving with a constant speed, the particle is still accelerating because it's now going to have only the radial component of its acceleration, which is called the centripetal acceleration, all right, which keeps that particle in the circular path. But if the particle is now moving with a known variable speed, that means that the magnitude of this velocity ladder is changing, and for this magnitude of this velocity changing, for it to change, sorry, there has to be a component of acceleration acting along this direction, and that component of acceleration acting along this direction is the tangential component of acceleration. So you realize that for this speed to be changing, for known uniform circular motion, the particle has both the tangential and the radial components of acceleration. So the acceleration of the particle is basically, the vector sum of these two components. And so you can actually calculate that as that, and then you notice that that is that. And so our answer is D. The particle has both tangential and radial acceleration because, of course, it's with a variable speed. Okay. Thermistors are usually made of, okay, thermistors, that this one is a giveaway question, of course, semi-conducting material with low temperature coefficient of resistivity. All right, so yeah, that one was a giveaway. The circuit diagram in figure 1 below shows a 6-volt battery connected across 3 resistors. The current I flowing in the circuit is, okay, the very first thing you have to notice with the analysis is that this resistor and this other resistor are actually in series, because if current flows here I, and then I is going to split into I1 and I2 flows into this first resistor, and then the same I2 that flows into this guy. So the same current flows through these two different circuit components. It means that those two circuit components are actually in series, and so you realize that we're basically going to get the resultant resistance for resistors in series, and you have that. And so our arrow total, therefore, for all the resistors now, because if I get the arrow total for those in series, is basically 6 plus 6, right? And now that one now becomes in power with this 6 ohm. So you have 12 and 6, and power, you get the arrow total by, of course, doing that. And so your arrow total now is 4 ohm. So the current is basically the EMF divided by the total resistance, which is basically 6 over 4, which is 1.5. Our answer is B. Question 5. Which of the following is the reason why a balance point may not be found in a potentiometer experiment? Okay, so we are just going to draw a potentiometer here. So you realize that this is our potentiometer wire. This E1 is the driver's cell. E2 is actually the test cell. And this is our galvanometer here. So you realize it's pointing vertically upward. It means that this is the balance length. XT is the balance length. And so this arrow basically regulates how much potential is available, or PD is dropped across the entire potentiometer wire. So if we reduce arrow, we're increasing the total PD that is available to be dropped across this guy according to the potential divider rule, right? Because this EMF is basically shared between arrow and the entire wire XY. Okay, so we can actually go on and then give the rules for a balance point to actually be found on this potentiometer wire. And so driver cell E1 and test cell E2 must be connected in opposition. Do you see that? Positive terminal to positive terminal. That's a necessary condition for a balance point to be found. Otherwise, there'll be a continuous flow of current here, and this galvanometer would never get to zero deflection, because it only gets to zero deflection when no current flows through it. Okay, so when the PD across XT is the same as the PD across E2, so you realize that two arms with zero potential difference between them, no current flows between them, and so that's why this guy does not deflect. So that is made possible by the fact that you've connected E1 and E2 in opposition, positive terminal to positive terminal. The next point is actually that your E1 has to be greater than E2. If the EMF of the test cell is greater than the EMF of the driver cell, then the test cell is always going to supply current throughout the circuit, right? And so you're never going to get a balance point. So it's very necessary that your driver cell is bigger than the test cell. And the next thing is actually that, which is basically, you look at it very critically, you realize that these two guys are very similar, right? So you notice that Vxy, that's the PD drop across the entire potentiometer wire, must be greater than E2, because if E2 is bigger than the PD that is dropped across this entire potentiometer wire, then you realize that you're never going to find a balance point. So if E2 is bigger than the potentiometer, the PD across Vxy, then what you have to do is actually lower this R, the value of R, so that more PD is dropped across Vxy. And so you notice that you might be able now to find a balance point that basically is equivalent, or maybe the PD across now Vxy might just be equal to E2. Then that becomes the balance point, right? And so these are like the necessary conditions to get a balance point. And so you can actually notice here that if this is the balance point, then our Vxy, right, Vxy must be equals to IRxy. Now this is just something you have to know, right? Because this is operating like a wire. This potentiometer wire XY is actually operating like a wire, like a resistor, sorry. So you notice that if we have a balance point here, then the PD across the entirety of XY must be what? The current that flows through this resistor multiplied by the resistance of the resistor, and the resistor is what? Rx all the way to Y. Perfect. And that's basically Ohm's law. And so you notice that our Vxy here is basically I. What is Rxy? Is basically rho L over A. So the entire length of this material divided by A, that is Vxy. Now it means that to get Vxt, that right, you have to multiply I by what? Rho L xt, right? So the length that gives me the balance point is basically xt, all that divided by A. So you realize that if I take this slider, I take it all the way up, I'm increasing the PD that is the PD that is dropped across the point xt, and so that might increase to a point where it matches E2, and boom, you get the balance point. Okay, so I just really need to talk a lot about this, but the answer is actually C. The PD to be measured is greater than the PD across the potentiometer wire. That's just what we've said now. So if this E2 is greater than the potentiometer wire, you're never going to find a balanced point. The period of a satellite in a circular orbit of radius r is t. The period of another satellite in a circular orbit of radius 4r is. Okay, so we're just basically using Kepler's third law there. T squared is proportional to r cubed, and so you basically produce an equation of proportionality there, and then you make T2 the subject basically, and so you replace T1, R2, and R1. So you notice here that R1 here is just R, and R2 is 4R, and then our T1 is basically just T. So you can simplify that, and then you notice that our T2 is 8T. So the answer is D. The mean square velocity of 5 molecules velocities, that is, okay, so I've just put it out here. So you have the mean square speed, which is basically the mean of the squares of C. Very important that you understand that that's what mean square speed means. Mean square speed. So you're finding the mean of all the squares of the speeds. So we'll find the mean of the squares of the speed by doing what? By squaring each of the speeds first and then getting their means now. So 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared divided by the total number of molecules there, which gives us the mean square speed as 15 meters squared per second squared. And so our answer is D. the internal energy of 1 mole of an ideal gas depend upon. Okay, so we're just quickly going to write down the first law of thermodynamics, mathematical expression. dq equals du plus dw, and you know that dq, of course, is the amount of heat supplied to the thermodynamic system, or the heat content of the thermodynamic system, and then du is basically a change in internal energy of the thermodynamic system, and dw is the amount of work done by the gas. And so our du, which is basically n c of p delta t, well, you're heating a gas, and so you can heat the gas at infinite numbers of heat capacities. So but the two most common heat capacities for gases are basically heat capacity at constant pressure and heat capacity at constant volume. So you can actually use the heat capacity for constant volume if the gas is heated at constant volume, which in that case would make the thermodynamic process an isochoric or isovolumetric process. And if you're heating the gas at constant pressure, like this equation is showing, so n c of p, which is the heat capacity of the gas at constant pressure, it means that we're heating the gas and that thermodynamic process is isobaric, okay, where the pressure is constant. And so our du, if we, for 1 mole of gas, our du is basically just going to be Cp delta T. And so you notice that another expression for at constant volume would basically be Cv delta T. And so you notice that the change in internal energy is only a function of what? Change in temperature, or the temperature of the gas. And so our answer is B. And that's why for isothermal processes, thermodynamic processes, you notice that the temperature is constant, and so the change in internal energy for such processes is 0. So du is always 0 for such processes. So dq is always dw. The heat supplied basically goes in to enable the gas to do work, right, for isothermal processes. So but you notice that Cp is actually greater than Cv, and is actually greater than by this amount. Cp minus Cv is equal to R, because I just talked about, you know, heating a gas at constant pressure and heating the gas at constant volume. But it's worth noting that the heat capacity of the gas at constant pressure is bigger than the heat capacity of the gas at constant volume, and it's a past UC question for candidates to be able to explain why the heat capacity of the gas at constant pressure is bigger than the heat capacity of the gas at constant volume. Just come back here. If you're heating this gas at constant volume, you notice that the gas does no work. dw is actually 0, because dw is p delta v. So if the volume is constant, the gas does no work. So all the heat supplied basically goes into the what? Change the internal energy of the gas. And you know that heat capacity is basically what? The amount of heat required by a substance to change its temperature by a unit change in temperature. And so you notice that if I'm supplying all the heat, that is simply going to change the internal energy, which is a function of change in temperature, then the heat capacity there becomes smaller. All right, it becomes a lot smaller. But for at constant volume, at constant pressure, sorry, where the gas actually does work externally because it's P delta V, you notice that all the heat you supply, part of it goes to enable the gas to do work, and only part goes to change the internal energy. And so it takes a lot of heat for the temperature of the gas to actually change by a unit Kelvin, or by a unit change in temperature. And so that's why the heat capacity at constant pressure is higher than the heat capacity at constant volume by this amount. Okay, so our next problem. B1, B2, B3 are 3 identical bulbs connected to a battery of steady EMF with key K closed. What happens to the brightness of the bulbs B1 and B2 when the key is opened? Okay, so the very first thing is when K is closed, you notice that if K is closed, then B3 and B2 are in parallel, okay? And so the PD drop across any one of them is basically equal to the PD drop across the combination of them. All right, and so when you get a combination of these two guys, because they are all identical, a combination of these two guys would basically be what? R over 2. And so you notice that the PD drop now across this guy would basically be PD drop across R over 2. And so you notice, how do you get that? PD is basically R over 2 divided by R over 2 plus R, because now a combination of these guys would now be in series with this guy, and the resistance of this guy is R. The resistance of the combination will be R over 2, and that's why we're getting the PD drop by simply getting the resistance of that guy divided by its resistance plus R multiplied by E. This is the potential divider rule I'm basically using here. And so you have VB2 is basically E over 3. Now you can go next and calculate VB1, all right? When this K is closed, what is our VB1? If this guy is already E over 3, which is the PD drop across the combination of them, then the PD that is dropped across this guy will basically be 2E over 3, because of course the EMF is shared between these two resistors, right? So we have that. Now if you go over here, when this switch now is open, you notice that B1 and B2 are basically in series, and when they're in series, they basically just share this EMF, and because they are equal, they have equal resistances, you notice that they share the EMF equally, E over 2, E over 2. And so you notice that VB1 moves from 2E over 3 to E over 2, which implies that B1 drops in brightness because you notice that the PD across B1 has dropped. And so VB2 moves from E over 3 to E over 2. B2 increases in brightness because the PD across that has also increased. And so our answer is A. The figure shows 2 point charges of magnitude that and that located at points P and Q along a straight line ST. So we have that. Just quickly, let me just make some points here, some clear points here for you to note for point charges like this in electric fields. If P and Q are similarly charged, then point of zero net electric field will be at a point between P and Q, closer to the charge with a smaller magnitude. So if P and Q have equal charge, okay, maybe both 2.9 microcoulombs, then notice that the point where the resultant electric field will be zero will simply be midway between them. All right, good. But if they are not, then the point will be actually somewhere between the line joining their centers, but closer to the guy with smaller magnitude, which is basically going to be closer to P here. Now, if P and Q are oppositely charged, the point of zero net electric field will be outside of the line joining their centers, closer to the charge with a smaller magnitude. So if this guy was negative and this guy is positive, then the point where the net electric field would be zero would be somewhere closer to this guy here. All right. Perfect. Again, you can just compute from Coulomb's law, and then you notice why I'm saying these things. All right, so our answer in this particular case is basically just D. A battery of e.m.f. E has an internal resistance R. A variable resistance R is connected to the terminals of the battery. A current I is drawn from the battery. V is the terminal PD. If R alone is gradually reduced to zero, which of the following best describes I and V? Okay, so we are actually just going to use mathematics to do this. So this is our diagram. Okay, so initially we can just calculate our I, right, which is basically the sum of EMF divided by sum of resistance in the circuit. So total resistance in the circuit is basically R plus R, right? And so you notice that total EMF is E, so it's divided by it, and then you notice that our current is this. And so you notice that if R is tending to zero, all right, because the question says we are gently reducing this R to zero, so our I would be increasing because this denominator is reducing now, so I is increasing toward E over small r, and so I increases. And so we have our V to be IR, right? V is basically terminal PD, PD drop across this external resistor. So you notice that is IR, the current that goes through the resistor multiplied by the resistance of the resistor. But that V means that the resistance of the resistor multiplied by current, and our current is this. So basically I have R over R plus R multiplied by E, because all of that is our current. And so you notice that if I'm reducing R to zero, then this numerator tends to zero, right? So everything collapses to zero. And so our V decreases to zero as R returns to zero. So our answer in this particular case is D. A body of mass to 4 kg is accelerated upon by a constant force travels a distance of 5 meters in the first second and a distance of 2 meters in the third second. The force acting on the body is... Okay, so the very first thing you have to notice here is that the particle must be decelerating. So these forces that were indicated here must be the magnitude of the actual force that acts on the particle. So the actual force must be negative force, right? For the particle to move 5 meters in the first second and then 2 meters in the third second means it's decelerating. Okay, so in the first second, U is actually 5 meters per second. All right, in that very first second, so it covers 5 meters in 1 second. So that's our initial velocity. In the third second, the particle covers the velocity of the particle now is 2 meters per second, right? Because it covers 2 meters in 1 second, which is the third second. And so you notice that our acceleration developed by the particle between the period of the first to the third second is actually V minus U over T. And so you notice that our V minus U divided by T, which is now 3 seconds from the first to the third second, the total time is 3 seconds. And so the magnitude of our acceleration is 1 meter per second squared. And so you notice that our force is MA, and so our force is basically the mass is 4, and so our force is 4 newtons. And so our answer is B. The beam of protons used in an experiment is referred to as being a 20 mega electron volt beam. The mega electron volt is a unit of, well, electron is actually charge, the electronic charge, the charge on an electron, and then voltage, of course, the PD. And so you notice that work done is what? QV, charge multiplied by voltage. So this must be work, this must be the energy of the unit for energy or work. And so you can also see that from quantum physics, where you say the kinetic energy of the photoelectrons is basically EV, right? of the electrons is basically EV. So you notice that, of course, boom, EV must also be the unit for work or energy. And so our answer here is A. This amount of heat is conducted through a 2-meter squared wall of 12 centimeters thick in 1 hour. Temperature difference between the two sides of the wall is 20 degrees Celsius. The thermal conductivity of the material of the wall in watt per meter per Kelvin is. Alright, so we just really need the equation for heat transfer. The Q of dt is Ka delta theta on L, and so our K is basically that. And so our K, you basically make the subject, and so the rate of heat transfer, heat is this in 1 hour, so you convert that time to seconds, so you have 3600, and then the length is actually 12 centimeters, you convert that to meters, and then of course our thickness or the temperature difference is 20 degrees Celsius, so you have your 20 there, and then our cross-sectional area is 2, that's why you have your 2 down there. So our K is basically 0.13, which is basically which makes the answer B. Which of the following phenomena can be used to explain the formation of rainbow? All right, I'm just going to put a diagram here. So you notice that there's a combination of a lot of things that result to the formation of a rainbow. A ray of light goes through water droplet, it gets refracted, and so when it gets to the water air boundary, it has to get refracted again. But now, if the angle of incidence is bigger than the critical angle of water, then it gets totally internally reflected, and so it bounces off the wall of that water droplet and then gets back to a different point. And so if the total angle between this incident ray and then this bounced off ray is up to 42 degrees, then you realize that dispersion occurs, and so you have white light basically spreading across the sky into all its various components, and you have red, orange, yellow, green, blue, indigo, violet. Of course, it spells out Rooigbave. And so this is basically a proof that our sun must be white. You know, in the STEM I gave them a question, what is the color of the sun? And the guys went like, geez, I've never thought about this, right? It's pink, it's a reddish, it's yellow, and all of that. Well, all of those various colors that we see when the sun is setting or when it's rising are only consequence of the fact that we have an atmosphere. Yes, those are just consequences of the fact that we have an atmosphere. And so when the sun is rising, notice that the rays are traveling from afar because it's low on the horizon, so the rays have to come from that distance all the way to Earth. And so before they reach Earth, a lot of their components have scattered off, right? All the various components with shorter wavelength, like maybe the violet, the indigo, the blue, the green, they have all scattered off, so leaving only rays of light or components of light with very long wavelength, which are like red, the orange, the yellow. And so that's why the sky appears to be reddish, yellowish when the sun is rising, and also when it's setting. You have to see the sky really reddish, and yeah, that's because the sun again is low on the horizon, and so the rays travel from a very long distance to get to Earth, and so a lot of those components are scattered off. And so when they strike the atmosphere now, these various components are scattered across the atmosphere, giving us the illusion that, oh, okay, so the sun must be red or something, of course. So the fact that the rainbow has this multi colors, right, tells you that the sun must be producing white light, and this white light now scatters into these various colors as a result of dispersion. So what is responsible for the rainbow formation? Well, there are 3 things. The very first one is refraction, the second one is this total internal reflection, and the third is dispersion. So dispersion is actually what spreads that spectrum of color across the atmosphere, and then refraction is actually what the principal core reason. So that's why refraction is our best answer here, and so our answer is B. Thank you guys so much for watching to the end. We hope that you enjoyed the video, and we are giving exams to upper seed and Form 5 students every month, so we want to make sure that these students actually get the best. And especially at our center, we have visions of producing at least 1225 points, and so we want to do everything we can in our power to make sure that we can achieve that dream. That's our 2023 dream. So what's yours? Hope you're putting in the energy and the tactic to achieving yours. And so we have a strategy, and the strategy is that every month we are getting standard KC mocks, and so students from anywhere can register and participate in those mocks. If you're in Form 5 or you're in upper SIF or you're in lower SIF or you're in Form 4, you want to test yourself with any subject, you can reach out to us, contact us with the contacts in the first slide, and yeah, reach out to us to discuss your registration. Thank you guys so much for watching. Keep working. We wish you all the best. We love you. Thank you.